For our periodic table notes, use this to fill out your note guide. So, periodic table, we've used it. We don't maybe know everything about it. We've done that on purpose, so you just know how to find stuff. But now we're going to explain how it's organized. It's very specific, and every single placement of every element is there for a specific reason. This guy over here, this picture, this handsome gentleman over here, some say it looks like Mr. Treese, but I don't know who said that. Anyway, this guy, Dmitry Mendeleev, he decided that the way we should arrange these elements is by their atomic weights and properties. He knew some elements existed, and he put them on the periodic table. He also left spaces or gaps because he assumed that eventually elements would be discovered that fit there based on what he knew about the elements that he already had. And indeed, he was right. So go ahead, press pause as you put this into your notes. We're going to see this all year, all the time. But if you notice, this was pretty nice because it's color-coded. We're going to learn today about the differences between nonmetals, alkali metals, transition, all of these different types of elements and why they are exactly where they are located in this table. So one way that they're arranged is by their atomic number. If you look here, the very first element here in top left green is atomic number 1. Go all the way across, and it's number 2. Drop down a row, 3, 4, 5, 6, 7, 8, 9, 10. So they're arranged by their atomic number, which is their number of protons. Remember, protons determine what kind of element you have. Those horizontal rows going across are called periods, and they also tell us something we haven't told you yet, the number of energy levels that the elements in that horizontal row or that period have. In other words, up here, there's only 2 elements in that top period because they only have 1 energy level, because they only have 1 or 2 electrons that fit on that first level. Drop down to period 2, and these elements all have 2 energy levels because they have 10 or less electrons. The next row has 3 energy levels, 4, 5, 6, and that's why it's arranged as it is. And this bottom one, which we'll never really deal with, has 7. Vertical groups, the up and down groups, are called families, and they will tell you how many valence electrons that group has. In other words, group 1A going down here. Well, this only has 1 electron, so it must be a valence, and everything else in this group has 1 as well. So if we look at the next one, lithium, 2 of those electrons will be on the first energy level, 1 on the second, and those will be valence. Everything in here. So if I gave you francium and said, figure out how many valence electrons it has, you don't have to go, well, of those 87, 2 are on the first level, 8 are on the second, blah, 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 and maybe make a math mistake. You could just say, hey, everything in this first row has 1, everything in this row has 2 valence. If you skip off to the other end, it's kind of, well, actually, let's go in order. 1 valence electron, 2 valence electron. We skip these, what are going to be called the transition metals, and go to where boron is. These all have 3, 4, 5, 6, 7, and then 0 or full. Like some say they have 0 valence. I prefer to say it has a full outer shell, whether that's 2, 8, 8, 18, 18, 30. It doesn't matter. This group over here is special. We'll talk about later, but they have a full outer energy level. You can read through that. Just again, periods are left to right, families and groups are up and down. So you have something in common with other elements, whether you're in the same up and down family or group or that period going across. Start getting in the habit of practicing and figuring out what is what. So if you're in the same period going across, you have the same number of energy levels for your electrons. Press pause and go ahead and put this in your notes. We said the up and down family or groups are going to tell us that they have the same number of valence electrons, which means later we'll spend more time on this. They react the same. Some elements are super reactive. You don't even find them alone in nature. They're always stuck with something else. Some never stick to anything else, and that's all based on the number of valence electrons that we have. And like we say down here, for now we're going to skip over those transition metals and not really worry about them too much. Remember our 2, 8, 8, 18, 32. This again, well, actually, let's look at fluorine. Fluorine has 9 electrons, so 2 of those are going to go in the first energy level, 7 will go in the second. What that means is everything in the up and down family that fluorine has also has 7 electrons. Elements want to have a full outer energy level, so if you're close, you have 7 and you need 8, you're going to be really reactive. You're going to want to pick up, find an extra electron to fill up your outer energy level and be what I call happy. So elements that have like 7 valence electrons can easily find one. They react super easily. Elements that only have 1 valence also reacts very readily and easily because they can get rid of 1 and then the level below it is full. Go ahead and pause this while you put this in your notes. So you should know this by now, but it never hurts to review. Our tiles of the periodic table. The smaller number, some will put it below, some will put it on top, but if it's smaller, it has to be the atomic number. It tells us the number of protons, also tells us the number of electrons. We'll have the symbol there and then what that symbol stands for, and the atomic mass, remember, is protons plus neutrons. So if you're asked to determine, round this to the nearest whole number, subtract the number of protons, that'll tell you neutrons. The reason you get decimals is it's a weighted average. In other words, if you look at this, this is very close to 12. 12 minus 6 is 6. That means most carbons have 6 neutrons. But there are some that have 7. If you found all the carbon atoms in the world and averaged them out, this would be the average weight of them all. Just another periodic table that we're going to explore a little bit more. All the metals, and we're going to show you here in a second where the metals are. Give you a hint, it's on the left side. That's the easiest way to remember it. All metals are conductive, meaning they let electricity and heat flow through them. They're malleable, meaning you can smash them into flat sheets, and they're ductile, meaning you can stretch them into thin wires. That's something that all metals have, and that's part of the reason they're put on the same side of the periodic table. So, our group 1, we don't count hydrogen. It's not a part of this. It is a gas. It's kind of weird, those top 2, hydrogen and helium. But everything in blue is an alkali metal. They are very reactive because they all have 1 valence electrons. They want to get rid of that and then be happy with a full outer level. Like all metals, they're malleable, ductile, and good conductors of electricity. And in fact, they're so reactive, if you mix them in water, they will explode. Which, this is a super short video, so I'll let you see. Here's lithium, sodium, and potassium, all alkali metals, and there's little pieces of them in this water.
This video highlights the increasing reactivity of the alkali metals as you move down the periodic table. Starting off with lithium, then moving into sodium, and finally potassium, which is the most reactive of these 3, which explodes as soon as it hits the water.
And you can see each of them caught on fire, and this is the order they are in the periodic table, and he said as you go down the table, the more reactive they are, and that's why potassium down here caught on fire the quickest, sodium and lithium kind of just produced gas bubbles. It was reacting.
This video highlights the...
Go ahead and pause here and put these into your notes. Group 2 here in red, these are also metals, but they're the alkaline earth metals. They're still very reactive, not quite as much as that first group, the alkali metals, because they have 2 valence electrons. Think of electrons, even though they basically weigh nothing, as like 100-pound weights. Is it easier to move 1 out of the house, like this group 1 has to do, or 2? Obviously 1, so they're more reactive than the group that has 2. They're actually harder and more dense than group 1. And they're reactive like the alkali metals, so much so that they're not found in nature. Free, meaning they're stuck or bonded with other things, forming molecules or compounds. Our transition metals, the weird ones that we're not going to talk a ton about, this big group in yellow, they're still ductile, malleable, conduct electricity and heat, shiny like other metals. They can put more than 8 electrons in their outer shell because they're filling up more than those first 3 levels often. And here's an interesting fact. Iron, cobalt, nickel, all transition metals, are the only known elements that produce a magnetic field. So transition metals have some unique properties amongst them. The bottom row that kind of gets pushed out of the periodic table because it would make it too long, are mostly man-made. They just find a way to add a proton, and as long as it's stable for a while, they can count it as a new element. But they're also radioactive, dangerous, and harmful to us. Other metals. You look up here, this light blue section here that forms like the steps, they call it, on the right side. These are also ductile and malleable, solid, and have high density as well. Not as reactive because we're talking about 3, 4, or 5 valence electrons, depending which of these groups we're at. All right, here's a weird group, this purple metalloids. Metalloids have properties of metals and nonmetals. Some of them are semiconductors, which means they can carry electricity under certain conditions, but not every condition. And that's one of the reasons they're used in computers and little microchips, because of this semiconducting ability they have. Nonmetals, now this green group, they're pretty much the opposite. Nonmetals don't conduct electricity. They're brittle, not hard, and they're dull, and they don't reflect light, not shiny. A lot of notes to copy here, so press pause while you put them into your note guide. If you want to, Google search physical properties of metals and nonmetals, part 1, but we're not going to show this here, so we can get you through this and caught up. All right, our next to last group here, group 17, this pink group, are called halogens. Halogen is a special name that means salt former, because compounds that have one of these halogens in them are called salts. And what's unique about these is they can exist in all 3 states of matter, a solid, liquid, or a gas. They have 7 valence electrons, so they're very reactive, and don't find them in nature alone. They're stuck with something. And finally, but not least, the orange group here, the noble gases. They don't form compounds at all. You pretty much always find them alone in nature because they have full outer energy levels. Their outer energy level is full, like all atoms want, so they don't react. So they're either called inert, I like to call them happy. Not a technical term, but it makes sense when you're learning this stuff. Again, Google search this if you like, but we're not going to play songs while you guys are catching up.
And now,
pause while you put this in your notes, and you should be good.